Is anything coming through here? Hello? Is anything coming through? Anyone out there hearing me at all or seeing anything? Is this all coming through? Is my audio coming through and the video now? Okay, good. All right. Sorry for all the hang-ups and delays. Yesterday, we had a snowstorm that took out our power lines, a heavy, wet snow. It's getting to be winter time. It's a little early this year. Anyway, my name is George Notchuk, as some of you know, and this is the first hangout that I've attempted. So kind of bear with me. I'm a newbie at all this. And it's going to be difficult to monitor the side chat along with the video because I'm by myself. So what I'm going to do is make my presentation for about 20 minutes, a half hour here. And then I'll look at the chat for questions, and I'll try to interact with you people in the chat as best I can. Like I say, I don't have any help on this. I'm just kind of doing this, winging it all by myself at the moment. I'm just kind of getting my windows set up here so that I can see what's going on. Let's see. Okay. I guess I can get started, hopefully. Again, name is George Notchuk, and what I'm going to do in this particular hangout, I have a rather aggressive agenda, and I'm not going to get through it all today, obviously. I was intending to do this yesterday, and our power went down at around 9 a.m., and I didn't get our power back up here until around 4 p.m., so I wasn't able to do the hangout yesterday, and this being Sunday, I'm not going to be able, I have some things going on a little later this afternoon, so I'm not going to be able to cover everything. What I'm hoping to do today, anyway, is set some groundwork for discussing buoyancy. I hope to get through most of that today, and I hope I may take a break and then at the last part discuss how we can use modern techniques for ranging the distance to the sun and how it's done. But all the other topics having to do with reference frames, Coriolis force, and the weight of a hourglass with sand falling, I'll do that at another time. So let's see. Okay, so Hey there, Cordis. Is the video and the audio coming through okay at this point? Maybe I've got to learn how to get people in here. And maybe in a little bit after I do my presentation, I can get you into the Hangout, Cordis, and we can talk about things. So let's see. All this is so unfamiliar to me. Like I said, this is the first time, and I've never done a Hangout. So trying to learn how to control everything is a bit of a challenge for me right at the moment. Okay, so in getting started here, the first thing that we need to do is understand definitions of terms as they're used in physics and engineering. It's very important so that we all understand the language, because most arguments having to do with technical issues always end up being based in definitions of terms. So I'm going to go through a number of number of words here, terms. I'm just going to find the limits on my board here. Let's see. That there. Huh. Something seems rather limited here. Yeah, that's a problem not running a test Hangout to begin with. End up kind of winging it on the air, and just be patient with me here. Okay. First off is the term inertia. Inertia is the tendency of a material object or body to resist changes in its position or motion. For example, if say you have a small rowboat sitting in the water, empty, you can give it a shove and it'll move fairly easily. Whereas if you try to move, say, a cruise ship or a big yacht, it takes a lot of effort. That's because of the inertia. It's a property of material objects that have mass. And what is mass? Well, mass is a property of matter that gives it inertia. The mass of an object determines how much inertia or resistance that object has to resist forces and changes in its position or motion. Like on the water here, if we have a small boat coming into the dock, one can stand at the edge of the dock and hold it back fairly easily. However, if you had a 30-foot cruiser filled with people and it's coming in, there's no way you're going to be able to resist it crashing into the dock. It just has too much mass, too much inertia for a single person to try to manage. Now, we also have volume. The volume is a space occupied by an object. And of course, we all know that if we have, say, a box, the volume is its width times its length times its height. So the volume is width, length times the height. We all know what volume is. It's just the space occupied by an object. Now we have density. Density is a definition. You don't prove definitions. I see this happening on these internets all the time in these discussions, people trying to prove things like, say, prove an angle or prove the radius of a sphere. You don't prove these things. These are definitions. You don't prove a definition. Density we designate by the Greek letter rho, and it is just mass per unit volume. That is, it's a figure of merit. It expresses the concentration or compactness of matter. That is the density. Now, another concept is force. This one seems to be causing some confusion for some reason. I don't quite understand it in listening to some of these shows and hangouts on the air. But let's go through what is meant by force and weight of an object. The force is a push or a pull that interacts and will change the motion of an object through its interaction with that object. So, say we have a mass sitting on the ground, and we have a person pulling on a rope. There's a force in this direction. Okay, so that's a pulling motion on that mass. This person is interacting with this mass and imparting a force to it that will cause it to move. Likewise, we could have another mass with a person sitting here pushing on it and pushing on a force in that direction. So it's a pulling or a pushing on an object that will impart motion to that object or change its motion or change its course if it is in motion. It's an interaction that's occurring. How about acceleration? Acceleration is a velocity, an object's rate of change of velocity. We designate acceleration by the small letter A, and it's the rate of change of an object's velocity. So it's the change in its velocity over a change in time. More technically, we consider it the time derivative of velocity with time. How velocity changes with time. And the units on this is meters per second squared. That's the units of acceleration. So for example, if I have, say, a curve, slide, and a mass, it will change its velocity in time as it goes down. It gains more and more velocity, hence it has an acceleration because the velocity is changing with time. Whenever you have velocity changing with time, you have an acceleration. Now, if the velocity doesn't change with time, if it's constant, then there is no acceleration. You can have an object moving with no acceleration. Any object that's moving with constant velocity has no acceleration. Because remember, acceleration is a change in velocity over change in time. And if we have a final velocity, we subtract off the initial velocity and divide by the time interval between those two. If these numbers are different, then we have an acceleration. But if the final velocity and the initial velocity are the same, then the difference is zero and there can be no acceleration. So any object in constant motion is not subject to acceleration. And this arises, the interaction between acceleration, mass, and forces is given by Newton's second law that we're all familiar with, that force equals mass times acceleration. Well, this isn't really how Newton stated the law originally. This is a simplified version of it. Newton actually stated that force is equal to the time derivative of momentum with time. That is, how does an object's momentum change with time? And that is related to its acceleration. Let's look at momentum. Momentum is just an object's mass times its velocity, and we designate momentum by the small letter p. Well, force is, through Newton's second law, is the time rate of change of momentum. And let's look at that, the more general statement and what that means. Okay, so force, according to Newton, is the rate of change of momentum with the rate of change of time. Well, momentum, remember, is mass times velocity. So if I'm going to take a change in momentum, there's two components to it. A change in momentum, or we use the Greek letter delta to represent changes. So this could be written as the mass of the object times the change in velocity plus velocity times the change in the object's mass divided by time. And then let's group. We have mass times the change in velocity over the change in time plus velocity times the change of mass over the change of time. There's two components to the rate of change of momentum with time. Well, most of the time, in most of the instances that we're involved with, the mass of an object does not change in the interval of consideration. Like you throw a baseball in the air, the mass of the baseball isn't changing. So we can solve for the dynamics of the velocity or of that baseball by just looking at its change of velocity with time. And this part we neglect because there is no change in mass with time. So that part goes to zero. And remember, we said that acceleration is delta v over delta t. So this equation reduces to that the force is equal to mass delta v over delta t, which is just mass times acceleration, which is the way it's stated in a lot of high school texts and stuff. But keep in mind, there's a second component to it that is most of the time zero because the mass of an object doesn't change. It becomes important, though, in rocketry, that as a rocket is going up towards space, it's consuming fuel. And as it consumes fuel, the mass of the whole rocket assembly is changing. So when solving problems like for rockets going into space, you cannot neglect this term because the mass is changing with time. So the momentum has two components to it, the change of momentum. Not only is the velocity changing with time, but the mass is also changing with time when we're dealing with rockets going up into space in rocketry. But for most problems, this term is zero and we neglect it. Now, let's look at forces a little more. Now, an object can have many forces acting on it simultaneously. The force in Newton's second law is the net sum of all forces acting on an object. So when we write force equals ma, this force is the net force, not just one force. So, for example, we can have, say, this block of mass sitting on the ground, and we can have one person standing over here pulling it. There's a force M1 that he's pulling it to the right, and we can have another person with a rope attached pulling in the opposite direction with a force M2 or force F2. There's two forces acting on this mass. Now, the force net, let's say forces directed to the right are positive. So we write this as F1 minus F2. That's the net force acting on the object. Well, if both persons here are pulling with the same force, the net force is zero, and the object isn't going to move. And Newton's second law shows us this. If the net force is zero, if this goes to zero, then the acceleration has to be zero because the mass is non-zero. The mass never goes to zero. The m is the mass of the object. So if the net force is zero, the acceleration is zero. If there's no acceleration, then the object's position cannot change. If it's in motion, it will remain in constant motion. There will be no change in its movement in space. Or if it's at rest, like on the ground, there's no net force acting on it. It's just going to stay at rest. It's never going to change. So that's what the statement here says, is that the net force is equal to mass times acceleration. Well, if F1 is a little bit greater than F2, the object's going to move to the right because this becomes non-zero, and F1 is a little bit greater than F2, so the net resulting force is to the right, so the acceleration is going to be in the same direction as the force and go to the right. And likewise, if the second person is pulling with a little greater force than the first person, then the object's going to move to the left, because if F2 is a little bit greater than F1, then this F net becomes a negative number. The positive direction is to the right. So negative number means it's in the opposite direction. So the object's going to move to the left if F2 is a little bit greater than F1. And the important point here is if the forces balance out, if F1 and F2 are identically equal in magnitude, the net force is zero, but there's still forces acting on the object. F1 and F2 are still acting on the object. In fact, it's going to try to stretch the object out. There's going to be internal stresses on this object with these two people pulling with a rope, trying to pull it apart. So the forces are there, even though the net force is zero. That is, that they subtract. It doesn't mean that the individual forces vanish. They're still there. It's just that the net force of acting on the object has vanished or gone to zero. So that's the important thing to keep in mind, is that if the net force is zero, it doesn't mean the individual forces acting on an object have gone to zero. It's just that their vector sums have gone to zero. Now, what determines whether or not an object's current movement changes or changes at all from a position at rest is the direction and the magnitude of the net force. That's the important consideration here. So if the net force is zero, then acceleration is zero, and there's no acceleration or change in the movement of the object. Forces and accelerations is what changes an object's movement. Conversely here, if an object is not accelerating, if the acceleration is zero, then the net force acting on it also has to be zero. It doesn't mean that there are no forces applied or all forces are zero. Again, it means that the sum of all the forces applied, the net force, is zero. That is, the sum has gone to zero. So, for example, if I have a mass m suspended by two ropes, there's a tension in this rope of force F2. There's a tension in this rope of force F1, and I've got another force, a rope attached, and I'm pulling downward, and the object isn't moving. What that means is that the vector sum of all these forces is zero, but yet these forces are still there. The object's being held up, even though I'm pulling down with force F3, it's not moving anywhere. These forces still exist. It's just that their vector sums have gone to zero. Hence, the object doesn't move because the net force is zero, so the acceleration has to be zero. And we write this as that the net force is the sum of the vector, the sum of the vector forces, and in this case, F net will be the vector F1 plus the vector F2 plus the vector F3. And in this case, if the object isn't moving, those all sum to zero. The object does not move, but it stays in position with forces applied. This is the subject of what is called statics. All engineers have to take this course called statics. There's statics and dynamics. Dynamics deals with objects in motion. Statics deals with objects that are not moving. They're staying put, like a bridge. All the members of a bridge. There's tensions, there's compressive forces, there's tension forces of the bridge members. There's forces in all the joints. There's moments on the joints. There's forces on all the members, but they all balance out. They all go to zero. So in statics, we're dealing with problems where the sums of forces is zero and that the sum of all moments is also zero. That is, things aren't rotating. If you have a moment, things will rotate. So sum of forces is zero, sum of moments is zero, is the subject of statics, like on a bridge. A bridge is remaining motionless. There's a lot of internal forces, stresses on that bridge, but it's not moving because the net sum of the forces is zero. Hence, there aren't any accelerations on any of the members. So the bridge does not move. Now, though an object is not moving, again, there can be forces external to the object that are still present and acting on the object. However, their influences collectively cancel out. Now, let's consider an object that is immersed in a liquid like water. I have a mass M. This is the surface of the water. There's a liquid in here, and we have an object immersed in the water. I'm going to take upward as a positive direction for forces. There'll be two forces acting on this object. There's what we call a buoyant force, and there's a gravitational force, which we call its weight. I'll be getting to this in more detail here in just a bit. This is just as an example to show you where we're headed. An object with mass M is in a state of what we call in a state of suspension. Suppose it's in a state of suspension. It's not moving. It's in a state of suspension while it's immersed within this liquid. We call this neutral buoyancy or buoyant neutral state. In this situation, there are two forces acting on the object, but they're equal and opposite. For a buoyant neutral condition, the buoyant force minus the gravitational force balance out in zero. So the net forces are zero. Again, F net equals mass times acceleration. If F net is zero, then there can be no acceleration. The object stays put. It's suspended. It does not move. We call that buoyant neutral. So there are no net forces in a buoyant neutral state. Because there are no net forces acting on the object to cause it to move. Now, so in this case, F net is FB minus FG, and this is zero. So the acceleration is zero because the mass is non-zero. There's no movement. This is by Newton's second law. No acceleration, no movement. So again, even though there is no net force causing the object to move, there are still two forces acting on this object. These forces don't go away. They're still there, even though the object isn't moving and it's buoyant neutral. There's an internal gravitational force acting on all the mass of the object, and there's also a non-zero buoyant force tending to push the object up. And we also have two buoyant forces, one on the top surface, one on the bottom surface. Well, the bottom surface buoyant force, I'll be showing you here shortly, is greater than the top. So these buoyant forces, with any object immersed in the water, these forces are still acting on the object and tending to compress that object. It's putting internal stress on that object. You know, like a submarine can only go so far down in the oceans to a dive depth before it gets crushed by the force. The forces are there, even though that say a submarine blows its ballast and is just hovering in a buoyant neutral condition up off the ocean floor, there's still forces acting on that submarine tending to crush it, to try to crush its hull and push the sides of the submarine in. The forces are still there, though the net force acting on that submarine down hovering above the ocean floor in a buoyant neutral state, that net force is zero, so there is no movement, but yet there are forces acting on that submarine, but they cancel out. The net force cancels out. Now, these forces, even though it's in a buoyant neutral condition, we could measure these forces, these individual forces, by planting what are called strain gauges, little semiconductor devices in this object, and we could measure these stress forces and parse all these forces out. Even though we don't see them, we don't measure them external. We can't measure them external to the object because they're canceling, but internal to the object, we would be able to measure them with strain gauges. Now, let's look at gravitational acceleration. Gravitational acceleration we call little g. G, for purposes of calculation, is generally taken to be 9.8066 meters per second squared. That's the gravitational acceleration. Now, forces can be exerted on objects not just by pushing and pulling, but also because they have mass by gravitational force fields acting on the masses of the object. Newton expressed this in a quantifiable manner in his famous equation that gravitational force between two objects is big G times the product of the masses divided by the separation distance of their center of masses squared. So if I have two objects, M1 and then M2, can be any shape, don't have to be spheres or cubes or anything. If I identify the center of mass of M1 and the center of mass of M2, then the distance between those two is the R that goes into the denominator. Big G is the gravitational constant, and that is 6.674 times 10 to the minus 11th. And the units on that would be, since we have to end up with newtons, these are kilograms, so G would be the inverse of kilograms squared. So we'd have kilograms squared in the denominator, meters squared in the numerator. So it'd be meters squared per kilogram squared times newtons. That would be the units on big G. Now, if M1, say, is the mass of the Earth, which is 5.9722 times 10 to the 24th kilograms, then we can substitute that in and write it this way. We have force is G, mass of the Earth, mass of the objects on the Earth, and R will be the radius of the Earth squared. So this is the force exerted by the Earth on an object standing on the surface of the Earth. Now, MEG, we could write this as mu of the Earth, mass of the object times radius of the Earth squared. Mu E is a product of big G with the mass of a planetary object. And this is called the universal gravitational parameter. This is known to a much larger degree of accuracy than either one of these two, either big G or the mass of the planetary object like the Earth. The mass of the Earth is only known to about 5 decimal places, whereas the gravitational parameter for the Earth is known to 9 decimal places. So mu of the Earth is 3.98604418 times 10 to the 14th. Why is it that this is known to a much greater accuracy than the mass of the Earth or big G? Big G is only known to about 1 part in 22,000, whereas we know the gravitational parameter to be better than 1/100th of a part per trillion. No, to 1 part in 4 parts in 1 billion, whereas big G is only known to 1 part in 22,000. Well, the reason for that is we can get these gravitational parameters very accurately for planetary bodies by orbiting a satellite around that body and precisely measuring the orbital period. And by knowing the mass of that satellite and the orbital period, we can very accurately determine the product of G times ME. So usually in these types of calculations, we go with the gravitational parameter rather than just big G and the mass of the Earth. Now, let's look at this a little bit further. Now, we have this expression that the force acting on the object is the gravitational parameter times the mass of the object divided by the radius of the Earth squared. Well, if you do this calculation, the gravitational parameter divided by the radius of the Earth squared, that just comes out to little g. This is just little g. So this is m0 times little g. So the force acting on an object is g m0. This is familiar. This is our force equals ma. This is the gravitational acceleration on the surface of the Earth. It has this value. And this particular force we give a very special name to. We call it the object's weight. Weight is a force. And that force, or the weight of an object, is just its gravitational acceleration times its mass. This is what a scale weighs. When you go into the bathroom and you weigh yourself on a scale, it's in essence doing this calculation for you and getting what this force is, the force of attraction towards the center of the Earth. And we call it the weight. So to recap, what we'll be doing now is using all these concepts and discussing buoyancy. And in another episode, I'll be talking about buoyancy in the atmosphere and the makeup of the atmosphere and why the atmosphere doesn't dissipate off into space and why it is not in violation of the second law of thermodynamics like some people want to claim, which is totally absurd. So the weight is the force exerted on a mass by the gravitational field, by a gravitational field, no matter what the source of that field is. We call it the weight of an object. The weight is just the force exerted by a gravitational force field on an object. It doesn't matter where the source of that field comes from. So to recap, we had a relationship relating density, mass, and volume. That is, density is mass per unit volume, which is a measure of the concentration of mass in a given volume. Then we have force, which is also weight, mass, and acceleration. And this is related through Newton's second law, that the weight or a force on an object is mass of the object times the gravitational acceleration. F equals ma, basically. Then we have momentum and velocity. And momentum is related to mass and velocity. It's just the product of an object's mass times its current velocity. And then we have forces, acceleration. Well, I already did that. Yeah. Force, acceleration, and mass. This is just the same as force and gravitational acceleration. In this case, we use a very special acceleration called the gravitational acceleration. All right. So I'll look now to see if there's any questions in the side chat before I move on to buoyancy and density and how we handle problems and how we analyze buoyancy. I'm going to derive buoyancy for you in a very simple way to show you where it arises and how we use it. And from that, we'll get Archimedes' principle. And then I'll, from once you understand these things, you should be able to analyze any problem at all involving density and buoyancy. It's just a matter of properly applying the concepts. Take a drink here. For those that know me, I'm back on the sauce, drinking Dr. Pepper again, except I'm cutting it back a little bit. I'm mixing half Dr. Pepper with half Pepsi. The Dr. Pepper, if I drink too much of it, it gives me leg cramps for some reason. So, but I'm back on the sauce. Okay, now going to discuss buoyancy. Buoyancy, we're going to use the concepts of mass, gravity, accelerations, forces. Remember, weights are forces. Now, let's consider water pressure. I'm going to first start off with water, but the concepts totally apply for gases also. The only difference is in water, in most liquids, they're incompressible. You can't compress them, so that the density of water remains pretty much uniform throughout the depth of the ocean. It does change a little bit, very slightly near the bottom of the ocean compared to the top, but it's essentially uniform. Whereas with gases, you can compress gases and change its density. So the problems become a little more complicated in solving, but the concepts are exactly the same as they are for liquids and immersing objects in liquids. Now, suppose we have a surface of water. This is the surface. And let's construct a little box that starts out at the surface that defines a column of water. Within this box, we have some mass of water within this box. We'll call it MW. From the surface of the water down to the bottom of the box, we'll call that a distance D. And also acting here, we have gravitational acceleration, our little g. This is the gravitational acceleration. That's always present. And for this discussion, we're going to assume G is uniform, doesn't change, is a constant value over the distances that we're dealing with from the surface of the water down to the ocean floor or whatever. It does change slightly, but it doesn't change that much that it's going to change the results here. And this is measured in meters per second squared. Now, all of the mass of the water contained within this box is pushing down with some weight on the water beneath it. And this should be easy enough to understand. There's a weight associated with the water within this box, and it's pushing down on the water that's at the bottom of the box beneath the column, and it's creating a pressure. That is, pressure, remember, is weight or force per unit area. This is force per unit area. That's what we call pressure. So this weight of this water within the box is pushing down on the water beneath it, creating a pressure. Now again, we're assuming a uniform gravitational acceleration over the depth from the water surface down to the bottom of the water mass, you know, maybe down in here, the lake bed, whatever. Now, volume, remember, we'll say that this is a box where the area on the top and the bottom of the box are the same. So the volume of the box is going to be A times D. Remember, the top surface of the box is at the surface of the water, and we're going down a distance D. So the volume contained within this box is just the surface area of the top and the bottom times the height of the box, which is D. The mass of the water is the density of water, we'll call it rho sub W, times the volume. And the volume is just A times D. Just substituting this in for there. Now, the density of water, rho sub W, is 1 gram per cubic centimeter, which is 1 gram per milliliter. A milliliter is a cubic centimeter. So that's the density of water. Or it's also 10 to the third kilograms, 1,000 kilograms per cubic meter. Okay, now, what's the weight? Our weight W. The weight W that's pushing down on the water beneath it is the mass of the water times the gravitational acceleration. Remember, force, which is weight, is mass times acceleration. Well, it's the mass of the water times little g. Putting in for the mass of the water, we have the density A, D, G. That's the weight pushing down. Or remember, A times D is just the volume. So I'll write this as the density of the water times the volume of this column times G. Now, the pressure, remember, the pressure being exerted is just force per unit area, or the weight per unit area. So I'll go up to here. So let's rewrite this. Is the pressure now is weight per unit area. Well, what's weight per unit area? Well, weight per unit area, if I divide each side by the area, we're just left with the density of the water times D, the depth to the bottom of the box, times G. So this is density of the water times G times the depth. I just transposed the D and the G here. Now, so this is the pressure here at the bottom of our container of volume AD that is containing the water. That's the pressure at the bottom of this box that's holding a volume of water with this mass density. Okay, now let's put in some numbers. It's always good to put in numbers when you're dealing with equations and stuff, to just see where you're at, to see if things make sense. It's always good to see if the theory is correct by putting in actual numbers and compared to reality. Well, the mass density of water in kilograms per cubic meter, I said, was 10 to the third kilograms per meter cubed. That's the mass density of water, or 1 gram per cubic centimeter. G, little g, is 9.8066 meters per second squared. And we have a depth D, which is in meters, measured in meters in this case. Now, pressure is measured in newtons per square meter. So if you do it, look at the units here, we have meters in D, which cancels with 1 meter here. So we end up with meter squared times meter. So we have, a newton is a kilogram meter per second squared. So these three gives us newton. Then we have meters cubed in the denominator and times meter. So we end up with meters squared. So that's an area. So the pressure is in newtons per square meter. And in the metric system, that's called a Pascal. 1 Pascal is 1 Newton per meter squared. So what is the pressure at some depth D in meters? Well, if we crank this out, this comes out to 9,807 times D. I'll write it here. 9,807 times D is the pressure in pascals, where D is in meters. So 9,807 times the depth in meters gives you the pressure at the bottom of that column of water. Well, 1 atmosphere is 101.325 pascals. This is the pressure of air at the surface of the earth. This is called 1 standard atmosphere. Now, let's calculate what depth of water, how far down from the surface of the lake or the ocean do we need to go to where the water pressure is 1 atmosphere, the same as 1 atmosphere. Well, all we do now is we take this, our pressure is 101.325 pascals. I'm sorry, the 1 atmosphere is 101.325 kilopascals, or 100,325 pascals, or this is 101.325 kilopascals. So 1 atmosphere is that many pascals, and we're going to equal 9 9807 times D in meters. Well, we solve for D in meters. So it's 101,325 divided by 9807, and this is meters, and this comes out to 10.33 meters. Or in the English units, this is 33.9 feet. So what this tells us is that for every 33, around 34 feet or 10.3 meters, you go in depth in the ocean or lake, you pick up the pressure of 1 atmosphere. So let's say you go down 1,300 or 1,033 meters. Well, 1,033 meters, we have the depth. We pick up 1 atmosphere for every 10.3. So what we're going to end up with here is 100 atmospheres of pressure. So at 1,033 meters in depth from the surface of the ocean, the pressure, the water pressure, is going to be 100 atmospheres. This is why submarines can't go too far down without getting crushed. Submarines are rated, their hulls are rated in crush depth. Depth beyond which you go, the pressure gets too great for the sides of the submarine to resist, and the submarine sides will breach, and the submarine will get crushed. So we pick up 10 or 100 atmospheres of pressure when we go down 1,033 meters. So for every 10.3 meters, you pick up 1 atmosphere of pressure. So to recap, we know now that weight is proportional to the mass of an object. The weight of an object is proportional to its mass by Newton's second law. Force equals ma. Now, so weight equals mass times acceleration, or on the surface of the Earth, it's its mass, object's mass, times the gravitational acceleration, or little g. So weight is proportional to mass. It's directly related. Double the mass, you double the weight. Half the mass, half the weight. Direct proportion. And the mass of the water is also related to its density and volume. That is, we have the mass of the water is equal to the density of the water times the volume under consideration. So these are some of the relationships. Now, I'm just going to take a half-minute break here to wet my throat and look at the side chat to see if, before I move on into buoyancy, if there's any questions. If anyone has any questions, post it now. I'll look at the side chat. You can troll me. I don't care. Trolls don't bother me. Trolls are welcome. Okay, now let's talk about buoyancy. Here I have the surface of the water, and I have a cube, a container, let's say a weightless container, just some infinitely thin membrane immersed in the water, and we're going to look at the amount of mass of the water contained within that container. Now, if we look at, say, this object straight on, we're looking at the front face. We look at the front face. These are the sides of the object. And this is the top, this is the bottom. If we look at the pressure, the hydrostatic pressure of an object immersed in the water, we have a uniform force or pressure along the top surface. The top surface is level, parallel to the surface of the water. Hence, at any given depth along a line parallel to the surface of the water, the hydrostatic pressure will be uniform. So that's indicated here. And if we go a further depth down, we just showed that the pressure of the water gets greater. So there's a pressure that's greater at the bottom of the object than at the top, and I will denote it by longer pressure lines. But the pressure at the bottom is also uniform because the bottom surface of this little cube is also parallel with the surface of the water. Now, how about on the sides? The pressure on the sides varies with depth. So we start out with the same pressure as we have here, and by the time we get to the bottom, it has to be the same as the pressure on the bottom. So what we have is a pressure that is uniformly changing linearly with depth along the sides. Now, this is our side pressure. If we sum all these up together, all these forces, this pressure over the side area, we get the side pressure. But we have symmetry here. The pressure differentials are exactly the same on the right side as the left side. So if we sum all these pressures up over the side area, we also get the same value as the side pressure is here. So that's what I have indicated here. The side pressure here on the left and the right-hand sides are exactly the same. What about the top and the bottom? Well, if I sum all the pressures over the area of the top surface, I get some force F1. And if I sum all the pressures pushing on the bottom area, which is the same as the top area, I get a pressure F2. But we know that the pressure is greater on the bottom surface than the top surface, so the force integrated, or the pressure integrated over the surface area to give us F2 has to be greater. The pressures on the bottom surface are greater than the pressures on the top surface. Hence, F2 has to be greater than F1. That only stands to reason. Now, let's use the equations that we developed. We have a pressure 1 at this depth D1. This is at depth D1 on the top surface, and the bottom surface is at depth D2. And the pressure down here is P2. Well, P1, the pressure, is the water density times the gravitational acceleration times D1 from the equation that we developed earlier. Hence, F1 is just going to be the mass density of the water times G times the area times D1. Pressure times area gives us force. So if I multiply each side here by area, I get a force. That's my F1. How about F2? Well, pressure at depth D2 is going to be the mass density of the water, G times D2. Hence, the force on the bottom surface is going to be the area of the bottom surface, which is also A. So it's mass density of the water times G A D2. So here are our forces that are on the top and the bottom surface of our cube. The sides are identical in area, hence the forces are the same. We can see that the forces are equal and opposite, so they cancel. So there's going to be no sideways movement of this object. This is, again, Newton's second law. Force equals mass times acceleration. The two forces, the net force on the sides, cancel. So this is 0. So there's no movement laterally on this object because these forces are equal and opposite. All the action is happening on the top and the bottom surface. Now, let's look at F2 minus F1. Well, let's see here. So I'm going to write F2 minus F1. Well, F2 is the mass density of the water, GaD2, and F1 is mass density of the water, GaD1. Okay, putting in these two values. Again, the top and bottom of surfaces are a constant depth, so the pressure on these surfaces are a constant. Therefore, the integral sum of the pressure over the surface area of the horizontal top and bottom surface is the hydrostatic pressure at that particular depth multiplied by the area. That's what these two are. So I'm going to factor out common factor here on both sides. So this is mass density of water, G A D2 minus D1. Well, what's D2 minus D1? Well, that's just the height of the object. The top surface is at D1. The bottom surface is at D2. D2 minus D1 is just the height of the object. Okay, so this is just the height of the object. So F2 minus F1 is equal to the mass density of the water times G times A times the height. Well, the difference between the forces acting on the top and the bottom surface is what we call the buoyant force. That is the definition of buoyant force. So F2 minus F1 is the buoyant force. F2 is greater than F1, hence the buoyant force is tending to push the object upward. F2 is greater than F1. This is a positive number. Positive will take positive forces upward. So the buoyant force is tending to push this object upward. Now, what about so this I'll also designate as just delta F. The difference in the forces between the top and the bottom surface is our buoyant force. And AH is just the volume of our box here, of the object that's immersed. So I can write this as the buoyant force is equal to the mass density of the water, G, times the volume of the box, of the object that's immersed into the water. Well, what's mass density times G? Excuse me. So let's rewrite this. Forget about that, what I asked there. Let's just rewrite this as the mass density times the volume times G. The mass density of the water times the volume of the box immersed in the water is what? It's the mass of the water that's equal to what would be contained inside that box if the box was hollow. So this is the mass of the water times G. The mass of the water that is displaced by this box times G is the buoyant force. Again, recapping, the buoyant force is the mass density of the water times the gravitational acceleration times the volume of the object. And I'm just putting the mass density of the water with the volume of the box, so that's the amount of mass of the water that would fit inside that box. So we have Newton's second law here. Force is equal to mass times acceleration. Well, what is this? Mass of the water times gravitational acceleration, that's the weight of the water by definition. The force that's acting, gravitational force that's acting on the water, we call it the weight of the water. So what's this statement tell us? The buoyant force is equal to the weight of the water contained within the box. This is a statement. This is Archimedes' principle. Well, what's Archimedes' principle tell us? It says that the buoyant force exerted on an object immersed in a medium is equal to the weight of the medium that is displaced by the object. That is, the buoyant force is equal to the weight of the medium, in this case, water, that would be contained in the volume of the object. So you don't have to go through all this stuff with densities and force differentials, pressure differentials. It all boils down to Archimedes' principle. This simple statement in analyzing any buoyant force problem. That is, the buoyant force is equal to the weight of the medium that is displaced by the object. So if the object, say, is several cubic centimeters, the buoyant force acting on that object is the weight of the water that would be contained in those cubic centimeters. So if I have some object, it doesn't matter what its shape is, could be an oddly shaped object, it has some volume, then the amount of water contained in that volume of that object, if I were to take the weight of the water, take the water that would be displaced by that object or contained within that volume of that object and weigh it, that is the buoyant force acting on the object. So this applies to any object because any shaped object can be approximated as a group of small little boxes like this. And the precision of the approximation increases with the number of boxes that you have estimating the volume of any oddly shaped object. Angled or curved surfaces do not nullify this analogy whatsoever, because the resulting force acting on any portion of a curved or angled surface, well, the forces acting on it can be split into two components, orthogonal to that surface. Show you what I mean there. Suppose I have an object kind of like this. And the pressure forces acting on the side coming in can be decomposed into two force components. One would be acting in parallel, and the other would be acting orthogonally or in the direction perpendicular to that side. Well, the component of force that's parallel has no effect on the object because it's parallel. It's not pushing or pulling on the object. And the component of force that's orthogonal or perpendicular to the surface is the important one. So we can decompose always our forces and then integrate over the surface. That is, what we do is we integrate the dot product of a force with a differential area where the differential area has a direction in the normal to the surface. What we call a normal to the surface is a vector that's perpendicular to a surface. So if we take a vector dot product between the normal of a surface and a force acting on it, it gives us the force component that's acting on the surface. So that's a thing you do in calculus, not important here. So what you do is you just integrate the dot product, vector dot product of the force vector with a surface normal over the surface. And it turns out that analysis that we did using the cube directly applies. It applies to any oddly shaped object. It doesn't matter what the shape of the object. The principle is the same. So when an object is immersed in a medium, gas or liquid, the apparent weight or actual weight measured within that medium is the weight of the object that it has in empty space in a vacuum less the buoyant force. Let's look at what I mean by that. So from Archimedes' principle, we know that the buoyant force excuse me, the buoyant force is equal to the weight of the medium. In this case, it would be water that's contained within the volume. I'll just write it this way. It's the weight if the medium fills the volume of the object. If we fill the volume of the object with the medium and weigh it in free space, or just the medium, we know the density doesn't change. So if we just take the weight of the medium that's in the volume of the object, that is the buoyant force. Now, when an object is immersed in the medium, like in water, you have some object. I've got, let's say, some object here. I'm immersed it in the water. We have a buoyant force acting upward, which is equal to the weight of the water that's contained within that object. Now, this object also has mass. If we take this object out of the water and weigh it, say, in the air, actually, we need to weigh it in a vacuum, but the buoyant force in the air is so small compared to the buoyant forces in a liquid, we can essentially neglect it. But strictly speaking, we'd want to weigh the object in a vacuum or in free space. But the difference between the weight of that object in free space compared to the weight in air is very minor and insignificant, except when you're dealing with extremely lightweight objects like foam or a helium-filled balloon. Then it becomes significant. But for something on the order of kilograms and more, baseball, rocks, whatever, the difference is so insignificant it doesn't matter. So when we put this object in, immerse it in the liquid, we get an apparent weight. The apparent weight is we have the weight of the object due to its mass. That is, if we take the object and say, measure it in space or in the air, in the atmosphere, get its weight, immerse it in the liquid, and then we weigh it again. In this case, what's going to happen is we're going to have an apparent weight, which is going to be the difference between the weight in free space and the weight in, well, it's immersed in the medium. So we have an apparent weight. The apparent weight is going to be the actual weight of the object in space or in the air less the buoyant force. So, as the buoyant force increases, the apparent weight of the object, that is, if I were to put a scale underneath this object, well, it's in the water. This is the surface of the water. And I put a scale and I put this mass on top of it. The weight that this scale registers is the apparent weight. It's going to be the free space weight of the object. That is, if we take the object and weigh it in our laboratory in the air and subtract off the buoyant force, then that is what the scale will register while that object is in the water. We call this the apparent weight of the object. The weight of the object in space or in the atmosphere is the true weight. It's the actual weight of the object. And the buoyant force, again, is related to the volume of the object and the medium that it's in. It's the weight of the medium that's displaced by the object when it's in, say, for example, in the water. And the actual apparent weight is the weight that we measure in this scale will have an apparent weight. So to get the buoyant force, if you want to know what the buoyant force is on an object, we just solve for the buoyant force and we make two weight measurements. One, we take our object, measure it in the lab, in the air, in the atmosphere, or in space, get its weight, and we subtract off the apparent weight. That is, we put the object in the medium, in the water, with the scale, we measure its weight while it's immersed, and we subtract that from the weight in the air in the laboratory. That's the buoyant force. The true weight, or the weight of the object in free space, never changes, whether you have it in a medium, not in a medium, whatever. This number stays constant. This is equal to the mass of the object times the gravitational acceleration. These don't change when you take the object from the atmosphere and put it in the water. This stays constant. So the free space weight, the true weight of the object, remains constant. What affects the apparent weight is the amount of buoyant force that you have on that object. Now, what do we mean by buoyant neutral? Well, the apparent weight of the object is the free space weight minus the buoyant force. Well, if the buoyant force is exactly equal to the free space weight, the apparent weight is zero. The object doesn't move. Again, remember, weight is a force. If this is the total net force acting on the object, force net is the apparent weight. And if that is zero, this is equal to the mass of the object times acceleration of the object. Well, if the net force is zero, there can be no acceleration. The object cannot move. So that's what we mean by buoyant neutral, is that the weight of the object exactly equal to the buoyant force. So there's no net force acting on the object, but there are forces acting on the object. There's the gravitational force acting on it, and there's the buoyant force. It's just that they just cancel. It's the external forces acting on the object canceling. Though they cancel, though the net force is zero, though all the forces acting on the object, like the buoyant force and the gravitational force, even though they cancel and the net force is zero, doesn't mean that those forces are zero, that those forces are still there. It's just that they're hidden because they subtract off and the object has no net force acting on it, so it's not going to move. It's just going to remain suspended in the liquid in a buoyant neutral condition. So that's what we mean by buoyant neutral, is that when the buoyant force of an object is exactly the same magnitude as its free space weight, such that so that they cancel and there's no net force acting on an object. I'm going to take a 1 minute break here to get a drink, and then we'll look at a few examples how to use these principles. Well, I see Kaiser Cube and Renee Angela are in the side chat. Shout out to both of you. Haven't heard from you in a while, Kaiser. I hope everything's going well with your new job and all. Okay, let's say we have a cylinder with different density liquids in it, and we've let it settle out so that the more dense medium will settle to the bottom and it will layer itself. This will happen like if you put oil and water and different alcohol and other things and color the liquids with food coloring, you will find that they will separate out. You'll have the more dense medium or liquid at the bottom and the less dense up at the top. Now, let's take, I see people like using an egg, and let's say the blue here is water. This is water. This is oil. And this is some other stuff, a heavier liquid like I think ammonia or something would be suitable. Sulfuric acid is heavier than water. But now let's take an object like an egg and we drop it in the cylinder. Well, what's going to happen is it's going to fall down because it's more dense and heavier per unit volume than many of the liquids here. It'll dive down, and then if it finds itself that there's some buoyant force by Archimedes' principle, let's say it's down here. We've got our egg down in here. Well, This egg has a mass. There's going to be a gravitational force pulling it downward, which is its weight in free space. We'll call that W of S. That's its free space weight. That is, if I took that egg, measured it on a scale in my lab, or say in your kitchen or whatever, that's the free space weight. And then we have a certain volume. This egg has a volume. Then the amount of this medium or liquid that's pushed out by that egg, if it turns out that the weight of this liquid that would fill that egg up is greater than the free space weight of the egg, there'll be a net buoyant force. There'll be a buoyant force upward. There's always a buoyant force. The question is the buoyant force greater than the free space weight? There's always two forces acting on an object. If we look at this object, we have a buoyant force that tends to push it upward, and we have a free space weight of that object. This always stays the same. This never changes. The only thing that changes is the buoyant force. The buoyant force depends upon the density of the medium that we're in, because remember, density of the medium times the volume is equal to the mass of that medium that fills the volume. And then if we multiply by little g, we get the force that's acting on the object. This is our our buoyant force. It's equal to the gravitational acceleration times the mass of the medium that is occupied by the egg, and times, that's what this is. That's the mass. The volume of the egg times the density of the medium gives us the mass of the medium that would be inside, that's occupied by that egg, and that's what generates the buoyant force. So this never changes. This is constant. That force is always there. So the question is what is the magnitude of the buoyant force? Because what we're looking at is the net force. The net force is the difference. So the net force is the difference between the buoyant force and the free space weight of the object. Now it looks like I'm off the screen there. Write that over here. So the net force acting on the object is the buoyant force minus the free space weight of the object. Now, if the net force is positive, that is, if the buoyant force is greater than the free space weight of the object's going to move upward. But if the net force is negative, where the buoyant force is less than the free space weight of the object's going to move down. It's going to sink. And if these two forces, the buoyant force and the free space weight, are equal in magnitudes, then we have a buoyant neutral condition. There's no net force, so the object's not going to move, because again, F equals ma. If there's no net force, this is force net. If the net force is zero, the acceleration is zero. There can't be any movement. No acceleration. The object has no acceleration. It's not going to move. It's going to remain suspended. So, all right, we've dropped the egg. It's going down into a dense medium. We find that the weight of the medium that's displaced by the egg is greater than the free space weight of the egg. Well, what's going to happen? Well, this is greater than the free space weight, so we have a net force upward. So the egg's going to rise. Well, let's say it gets up into here. Now, what happens? Well, again, the free space weight remains constant. This doesn't change. The only thing that's changing is the buoyant force. As that egg moves up, the buoyant force is decreasing because the buoyant force is equal to the weight of the medium that's displaced by that egg. The volume of the egg remains constant. So as we move up, the weight of the liquid, the weight of these mediums is decreasing as we move upward on a given volume. If I scoop out a little bit of the liquid here and put it in, say, a measuring cup of constant volume and do the same here, I will find that the weight of the medium down here is greater than the weight here. Hence, the buoyant force is greater down here than it is here. So as the egg moves up, the buoyant force is decreasing. Well, as this decreases, it starts getting closer to the free space weight of the object, to where if it overshoots, the buoyant force will become less, and we end up with a net negative force pulling it downward. So then it will move downward until the buoyant force is equal magnitude to the free space weight. And when that happens, the net force is zero. The egg will come to rest. It will remain suspended in a buoyant neutral condition because there's no net force acting on that egg. The buoyant force is equal and opposite to the free space weight of that object. And that's how an egg in a graduated cylinder with different density liquids behaves. And you can use this principle for analyzing any buoyant force problem. All you have to do is invoke Archimedes' principle. That is, that the buoyant force is exactly equal to the weight of the medium that's displaced by the object that you have in there. And then you compare that to the free space weight of the object. If the buoyant force is greater than the free space weight of the object will move up. If the buoyant force is less than the free space weight of the object will move down. Objects always move in the direction of the net force. And also keep in mind that in buoyant forces, I don't have the diagram up, but remember our cube that we had immersed in a medium. We had a force, two forces acting on the top and the bottom surface. The buoyant force is always in the direction from high pressure to low pressure. So the buoyant force will be in this direction upward because F2 is greater than F1. The pressure 2 is greater than pressure 1. So buoyant forces always are in the direction from high pressure to low pressure. And some of you may have done this demonstration to show it. Is say you're in a car with the windows closed so you don't have any air currents inside the car, and you have a helium-filled balloon. Now, a phenomenon occurs. Say we have our car, and it's enclosed. The windows are closed up, and you're sitting here in this driver's seat, and you're accelerating. You step on the accelerator, so the car is lunging forward with some acceleration. But what happens to you? You get thrown backward into the seat. And say you have a helium balloon tethered with a thread. What happens to it? It moves forward. You move backward, but the helium balloon moves forward. Well, why is that? Well, that's very easily explained using these principles. It's when the car is accelerating forward, before you start accelerating, if the car is just sitting, all the air distributes itself evenly in the compartment. It's uniformly distributed, equal density everywhere, the same density. When you accelerate, all these air molecules have some mass. They have inertia. So they remain in position. The car is lunging forward. So what happens is the air molecules are concentrated, are moved backward, so they're denser on the back of the car than they are in the forward part of the car. Remember, buoyant forces act in the direction from greater density to less density, or greater pressure to lower pressure. Greater density here, so we have a higher pressure acting on the right side of the balloon. We have a force F2 there, and then we have a force F1 here. But F2 is greater than F1 because the air is denser on this side of the balloon, on the right side of the balloon, than it is on the left side of the balloon. So there's a buoyant force acting horizontally. So the balloon moves forward. So not all buoyant forces go up and down. They can go in any direction depending upon how the density distribution is in the medium. In this medium where we have air, the distribution is when you're accelerating the vehicle, there's higher density on the rear end, in the rear of the compartment, than there is in the front part of the compartment, and the balloon will move forward when you're accelerating forward. So anyway, that's that. What I'm going to do, I'm going to keep this up. Excuse me. And I'm going to address how we measure the distance to the sun using modern methods. I'm going to just take a break. This spray, even though it's biodegradable, for some reason it really bothers my throat. So I'll be back in 5 minutes. Just so that I guess we'll see here. I'll hang something so you know that it's still here. So you're not just seeing a white screen. All right. I'll be back in 5 minutes or less. Oh, God. I tell you, boy, that spray really affects me. Be right with you in a second here. Just trying to get something set up. Yeah. What's going on here? Okay. Oops. Shoot. This thing keeps popping up. All right, what I'm going to be discussing here is this test that was done back in 1958 and 1959, and it's been published in Science back in 1960. It's called Radar Echoes from the Sun. Man's first direct contact with the sun opens new approaches for the study of solar events. I also have another paper that's more recent than this, but this was the first time that it was done. And I'm going to go through what these people did, how they did it, the signal processing that they used, and the measurement technique. So if you want to look up the paper on your own, it's in Science Magazine, volume 131, number 3397, 5 February 1960. And it's 4 pages worth. And I will, at the end here, I will post it on my whiteboard and zoom in on it and leave it up for a few minutes. So you can read the first page if you want. But this is the this is the article or the test. The paper that I'm going to go through now is this one right here. Let's see, we'll stop sharing. Okay, here we go. All right, we go through this paper now of how we radar distance the sun distance from the Earth. Now, this is very similar to what you'd be using like a carpenter's laser level. A carpenter's laser level is a radar in a sense. It's what we call a Doppler radar. It sends out a light beam and modulates the light beam and looks at Doppler shift to compute the distance from the laser to the target and back. And it's all, they're all based on laser or radar principles. In a radar, you send a signal out at a target. Some of the signal reflects back from the target, and you time the you time the propagation interval from when you send the signal out to when you receive it. And we know precisely what the speed of light is. We know it to a great degree of accuracy, to at least a part in a billion. And even back in 1960, they knew the speed of light to a great deal of accuracy. Since this is all based on knowing accurately the speed of light, I'll show you how you can easily determine it. Right in a laboratory, right in your own home. I do it every year for high school students. I measure the speed of light for them. And the way you do it, very easily, is you get yourself a high-speed oscilloscope, a few phototransistors, a light source, and you do this. An oscilloscope, for those of you that don't know what it is, it's an instrument that displays on the screen amplitude versus time of a signal. And you'll have some connectors. And modern day oscilloscopes are what we call sampling oscilloscopes. I have several of these. This one that I use samples at 2 gigasamples per second. That's 2 billion samples per second that it takes and reconstructs the waveforms. The time base on this what's important is what we call the time base. That is, with what resolution can you determine the time? Like if you put a signal in here, you have a waveform, let's say some pulses, whatever. What you're doing, the time base establishes the interval of time between events on your waveform. And you have little cursor markers that you can move around, and the time base is calibrated, and you can measure time intervals very easily. The time interval on my scope, my oscilloscope, is an HP 54825A. Any of you want to look it up? It has a 2 gigasample per second sample rate. And the time base, you can set it down to easily 10 picoseconds per division. And going across the whole screen, you can have that be on your, say, 50 picoseconds, from 0 on out to 50 picoseconds. Pico meaning 10 to the minus 12 seconds. A picosecond is 10 to the minus 12 seconds. Or 0.001 nanoseconds. In the laboratory, speed of light travels at, in the air at 11.8 nanoseconds. Or, I'm sorry, 11.8 inches per nanosecond. That is almost a foot per second. Light will travel about that distance in 1 second, 11.8 inches in a nanosecond. So this oscilloscope is more than adequate for timing the speed of light, because I can say at a 50 picosecond time base, 50 picoseconds is 0.05 nanoseconds. So that's 20 times better resolution than we need to measure the speed of light traveling 1 foot. So what you do is this, is you take your light source and you set it up. Doesn't have to be anything real sophisticated. A light bulb, incandescent bulb works fine. You can do it with a laser. But anyway, what you do is you set out a ruler, say a meter stick. You have 0 here. You have 1,000 millimeters here. And let's just say back here someplace, we set up our light source. And we have something, a shutter, to block the light source. Then you take a phototransistor. A phototransistor is a device indicated like this. This is the schematic for a phototransistor. Is the base of the transistor, doesn't have any leads. It just has a an area in the silicon that light strikes. The light strikes the base of the transistor, frees up some, dislodges electrons, and they begin to flow. And the device, you can put it in a circuitry with power supply and some sensors or probes, and you can measure the intensity of the light. Basically, the light striking the phototransistor is converted into a voltage or a current. And if it flows through a resistance, you can measure the voltage. That voltage can be measured on your oscilloscope. You take your 2 channels of your oscilloscope. You have a phototransistor, say, set up here. I'll just write it this way. with some circuitry, and we come with a lead, our probe, into the oscilloscope. Then, say some distance away, let's say at 1 meter away, or let's just go say at let's say we're at 500 millimeters or 50 centimeters away. 300 millimeters is about a foot. This is about a foot and a half, 500 millimeters. And say we set up another phototransistor and circuitry there. And we probe into the oscilloscope, 2 channels. So what we do then is we open up the shutter, let the light, the photons emerge, and they're traveling down this way. Photon hits this phototransistor, and what you'll see is basically a pulse. Or if you open and close it, you'll see a pulse with the response of that phototransistor. A little time later, those same group of photons or other photons hit this phototransistor, and you get another pulse from that channel. And all you have to do is, with your time base, set up your cursors and measure the time. And knowing the distance between these 2 phototransistors, we've got our distance is, say, 500 millimeters. And say we measure a time interval, delta t, some value, then the velocity of the light is the time it takes to travel 500 millimeters. So the velocity of light will just be the distance, 500 millimeters, over the time interval that we measure on the oscilloscope. And it always comes out within 0.1% or so of the correct value for the speed of light. The precision with which I can measure this depends upon how accurately I can set up the distance between those phototransistors. It's easy to get it within, say, 1 millimeter of 500 millimeters. So 1 out of 500 is about 0.2% in establishing accuracy of distance. So we can easily measure the speed of light to well within 0.2% using this, and to a much greater degree of precision if we could set these distance between the phototransistors up more accurately. But it's very easy to do, to measure the speed of light. And the way you calibrate this, you can say, well, geez, you know, we've got response times on the cables and all that. Well, that's easily nulled out. All you have to do is move the phototransistors together. Say, take this phototransistor and mount it over here so that they're both in line. You got the circuitry, and we move that probe over there, and then we hit them with light. And then what we can do is any delays between the 2 lines can get nulled out. You can just store that away and subtract that off from the actual measurement, because this is what you'd call an auto zero process. Is you put the 2 phototransistors together and look to see if the responses, if the cable lengths aren't exactly equal and the response times of the transistors aren't equal, you'll see a little bit of change between the pulses that come from each of these phototransistors when you hit them with light, when they're exactly lined up. And you can subtract that out, that time difference out from your final measurement, and get an accurate measurement for the speed of light. Okay, so that should answer any objections to how do we know the speed of light. That's one way we can measure it. And to know the speed of light within a couple tenths of a percent is more than we need for doing this experiment to range the distance to the sun. Because, I mean, even if you range the distance to the sun within 1%, no big deal. If the distance to the sun is 150 million kilometers and you get it to within a million kilometers, you know the sun isn't going to be 3,000 miles away. You know, you're going to be at 150 million kilometers plus minus a million kilometers, one over out of 150. So, you know, the sun's way out there. You don't have to have a high degree of precision to do this stuff. All we want to know is, you know, within, you know, ballpark figures, how far away the sun is, you know, whether or not it's a few hundred kilometers away or it's way out there. So, okay, radar echoes from the sun. These guys were pretty clever. What they'd done is they first had to determine what frequency of radar to use. They're going to send pulses to the sun, RF signal pulses, and look for the return echo. You know, that's how radar works, is you have a transmitter and you have a target and you send a signal out. It hits the target, some of it reflects back, you catch it in your receiver, and you time the distance. Or you make a time, you time how long it took from when you sent the signal out to when you received it. So the distance, the time from when you send it out to when you receive it is twice the time. Because you have TD going out, TD coming back. So by taking the speed of light, the distance to the target, D, then will be the speed of light, C, that we measured, which tends to be 11.8 inches per nanosecond, or 300 million meters a second in metric, and we multiply by 1/2 or by TD. I'm sorry. TD is the time that it takes to go from the transmitter to the target. That's TD. So the distance is just the speed of light times the time. Well, TD is just 1/2 of the total return trip. I'll call it return trip of the light trip. So TD will be the return trip of the light trip, light travel, divided by 2. That is the time that it takes. We send the pulse out, hits the target, comes back. That total time is RTLT. We divide it by 2 to get TD, multiplied by the speed of light. That gives us the distance to the sun or to any planets. If you want a radar range distance, say to the moon or to Venus or to some other planet, that's what you do. Okay, so that kind of sets the scene for the story. Now I'll tell you the story. It's actually pretty nice. Pretty clever of these guys. Okay. First, they had to determine what frequency to use. And the way they did this is they looked at plasma physics, knowing some of the nuclear processes that are going on in the sun and the corona and that. The problem that you have is you can't use a real high frequency to radar range the sun because of the noise generated by the sun in that frequency range, and the fact that the corona absorbs a lot of the signal before it hits the reflective area of the sun. And they determined that the optimum frequency to use is 25 25.6 megahertz. That's the frequency of their transmitter. Fairly low frequency. It's Citizens band radios at 27 megahertz. So it's right below the CB band. And they determined that they will end up with least amount of absorption of the signal in the corona if they use that frequency. Well, the problem with low frequencies is to have an antenna of any gain, you have to have an extremely large antenna physically. The gain of an antenna is basically closely related to its physical area divided by the wavelength of the frequency that you're using. Well, the wavelength of 25.6 megahertz is going to be somewhere around 12 meters. Very long wavelength. That's close to 40 feet in wavelength. And for an antenna to have any appreciable gain, you have to have an aperture area of several wavelengths, like a parabola dish antenna. They tend to be on the order of tens to hundreds of wavelengths in size. Well, you can't use like a parabolic dish to get any gain at those particular frequencies. So what they did is they built an antenna array using rhombic antennas. And they had 4 of them. A rhombic antenna, you tend to end feed them. And they had 4 of them in an array, tuned to this frequency of 25.6 megahertz. So when you build an antenna array, what you do is you phase them. So you're going to have some transmission line. You got a combiner here where you're going to feed the transmission lines, and you choose the length of these feed lines into the antennas to give you the proper phase relationship. So that when all is said and done at 25.6 megahertz, you will have a antenna pattern characteristic that will look something like this. You'll have some side lobes and a little bit in the back, but most of the gain is out the front end. And you can end up with a very narrow beam if you phase these things properly. They estimated that the gain of this array was around 25 dB above an omnidirectional antenna. But these are physically large, these rhombic antennas, in order to get any sort of gain. The antenna array was covering a rectangular area of 800 by 725 feet. That's how big this antenna array is. Huge. So then what you do after you combine them, you go into a TR switch, which means a transmit-receive switch. Basically, a transmit-receive switch is just a double throw single pole switch. What you have is you have your transmitter here, you have your receiver here. You use the same antenna and you switch between them. So what you're going to do is send out a bunch of pulses with the transmitter. So you switch over to the transmitter. They send out a string of pulses that have a period of 1 minute, 30 seconds from high, 30 seconds low, 30 seconds high, 30 seconds low. And they did this for 900 seconds. Well, knowing that we know about the sun is being out at 150 million kilometers, the time to send a signal from the Earth to the sun is about 500 seconds. Very close to that, within a few tenths of a second. And once it hits the reflective surface of the sun, it's going to take another 500 seconds to come back. So the total round trip is 1,000 seconds. So they send this pulse string out for 900 seconds and then shut it down. And then in that 100 seconds before it comes, we receive the signal back. They throw the TR switch over to the receiver, shut down the transmitter, and start listening for the return pulse. Now, so they have 50% duty cycle, meaning it's on for 50% of the time, off for 50%, on 50%, off 50%. And like I say, the period of this square wave being sent is 1 minute. So in 900 seconds, you're going to end up with, let's see, what is it? About 700, let's see, 30, gosh, what am I saying here? Yeah, excuse me. So anyway, we send out this pulse train for 900 seconds. Now, it was also determined, because of the relative velocity of the sun and the Earth, the calculated Doppler shift that would shift the frequency was less than 25 hertz. Let's look at that a second. Now, here we have, say, here's the sun, and here's the Earth orbiting about the sun. Okay, we're going to send a pulse out, this pulse train out, and somewhere within the corona of the sun, there's the reflective area, and the signal is going to come back to Earth. Well, some people have objected that by the time it comes back in the 1,000 seconds to travel out and back, you're going to miss the Earth. That's not true. The Earth hardly moves with respect to the sun in that 1,000 seconds. Remember, the Earth, with respect to the sun, moves about 1 degree per day. 365 days to go around the sun, so it's about 1 degree per day that the Earth moves relative to the sun. So in the 1,000 seconds, the round trip is about 17 minutes, which is 1,000 seconds. Well, how much is the Earth going to move with respect to the sun in that time? Well, we have 1 degree times 17 minutes, and then it's 1 degree per day, so that's 24 hours times 60 seconds, or 60 minutes. 24 hours times 60 minutes. This is how many minutes. So the ratio works out to 0.012 degree. So the Earth, with respect to the sun, in that 17 minutes that it takes to send the signal to the sun and receive the signal back, the Earth has moved less, a little more than 1/100th of a degree. So nothing's going to get missed. The Earth hardly moves at all with respect to the sun during that time interval. Now, they conducted these tests on the 7th, 10th, 12th of April in 1959. And they did a lot of signal processing. they sample, what they did is, remember, the carrier frequency is 25.6 megahertz. And what they did is the received signal comes into a mixer. You have a local oscillator, and you mix it down to 2000 hertz. So the 26.5 megahertz is coming in, you mix it down, and the signal bandwidth that you're looking for in the intermediate frequency is a very narrow band frequency from 0 to 2000 hertz or 2 kilohertz. And so you can filter out a lot of noise by having a very narrow bandwidth like that. So that's one way to filter out a lot of noise. So they're looking for this signal at between 0 and 2000 hertz. And you have a pulse train coming in at this intermediate frequency. And you have 30 seconds that it's on, 30 seconds that it's off, and so on. For 900 seconds, you just do this pulse train. Now, they use the Nyquist criteria for sampling. They use the sampling of this received signal. Well, what the Nyquist criteria is to totally reconstruct an analog signal from digital form. You have to sample at a minimum of twice the frequency that you're looking to reconstruct. So if we're trying to reconstruct from a bandwidth of 0 to 2000 hertz, we have to sample at 4000 samples a second. So that's what they did. And then at 4000 samples per second, you end up with 60 points per period. And you do this for 12 intervals. So you get 720 points. And what they did then is with the sampling, for each point, they averaged 30 points. Or no, 60 points. They did 60 averages of samples per period. So they sampled to get 60 points per period. And where each sample point is the average of 4,000 data points. So each one of these points is sampled at 4,000 samples a second. You average them, so that again filters out a lot of noise, the averaging. Statistically, if you have the number of samples, the amount of noise reduction you get is related to the square root of the number of samples that you take. So say you do 100 samples. If you do 100 samples, the filtering you get is a factor of 10, better. Well, here they're doing 4,000 samples. So the effective noise reduction they're getting additionally through the sampling is just the square root of 4,000 samples. So you get about a factor of 60 noise reduction just due to the averaging your sample points. And then you pick up more noise reduction because of the limited bandwidth that you have after down converting the signal that you're looking at. So with all this averaging to get rid of the noise, they reconstructed the pulses. And over the 3 days that they did this, in April of 1959, and if you look on, I'll just tell you with the page, this is page 330. They ended up after the averaging on the 7th of April, 1959, they had something that came in that looked like this. This was on the 7th of April. On the 10th of April, the signal looked something like this. And on the 12th of April, looked something like that. Now, when they averaged and composed all of these, they got a signal. The end result looks something like this. Now, if they were indeed receiving the signal in the ideal case, the theoretical ideal would have looked like this. A very good fit. They were 100% confident that they were indeed receiving the echo back from the sun. Now, to show you a little more of how they got this and the signal processing that was used, they don't tell you in the paper, but from the description of how they're adding and averaging the data, it's obvious that they're doing a mathematical convolution. A mathematical convolution is a wonderful way to pick a signal out of noise. And basically what they did is with all these sample points, you can read about it in the paper, they describe it, is you have these pulse trains that you receive back. Okay, they're going to be maybe down in the noise. There's going to be a lot of noise associated with them. And what you do mathematically is you put in your signal processing the ideal square wave that you're looking for. And then what you do is you pass mathematically, you slide each one of these pulses by. You start out with this pulse here, and you move it in this direction, and you integrate. This is a convolution. As this slides by, you're adding and subtracting data from the ideal, from subtracting the actual received data from the ideal as this thing slides by, and you end up with, through convolution, it gets rid of a lot of noise for you. And it tells you whether or not what you're receiving is correlated to the ideal pulse. It's a correlation scheme, statistical correlation scheme. And this is what they did, is in here they describe it, says cross-correlation curves that result are shown in figure 1. That's what I just showed you. They said here, the recordings made on 7, 10, and 12 April at 0 to 2,000 cycles per second were sampled electronically 4,000 times each second, and thus the data were converted from analog to digital form. The longest echo time common to the 3 days is 12 minutes or 721 second sums. So they ended up getting 12 minutes of good data on each of the 3 days in which to do these correlations. This is a square wave period, 1 minute, representing the transmitted wave was cross-correlated with the 721 second sums for each day. That is, the sums 1 through 30 were added, 31 through 60 were subtracted, 61 through 90 were added, and 691 through 720 were subtracted to obtain 1 point of the cross-correlation curve. The next point was obtained by adding the sums 2 through 31, subtracting those from 32 through 61, and so on. So what they're describing there is they're sliding the signal in time and summing it with the ideal curve. That's called convolution. Okay, so you find correlations that way. So anyway, the bottom line is they came out with a distance to the sun of the known established value of 150 million kilometers to the sun. And they were also able to, they had talked about what got them going on this is they state here the dramatic beginning of radar probing beyond the moon was announced last year. This would have been in 1958 when scientists at Lincoln Laboratory of the Massachusetts Institute of Technology described the first radar detection of Venus. A relatively low radar frequency is needed to avoid extensive absorption in the solar corona above the reflecting points. It was estimated the optimum frequency is near 30 megahertz. Much higher frequencies can be used to detect planets. So higher antenna gain can be obtained for given antenna size. I already talked about that. So like for planets and the moon and stuff, you can use much higher frequencies for doing the radar ranging and end up with more efficient physical size antennas for getting reasonable gains. But this was interesting. They went through the computations and they said because of the sun's size and despite its distance, a solar echo is 100 times more intense than the echo from Venus. So it's very easy to radar range the sun. If we can radar range Venus, we can certainly do it for the sun because the return signal is coming back because of the sheer size of the sun in spite of its distance is 100 times more intense than the signals coming back from Venus. So anyway, if anyone's claiming we don't know the distance to the sun, clearly they are wrong. This was done as long ago as in 1958, and I have some more recent papers where they're using these techniques to study the sun's corona. So this stuff is not that difficult. It just takes some patience and care. You have to have a lot of area, of course, to set up your antennas to work at those frequencies. But back in 1958, the technology was basically tube receivers and transmitters. We have much lower noise electronics now, much better ways, much higher sampling frequencies, better signal processing. So this is just a piece of cake anymore compared to what was done in 1958. Gosh, we're talking what, 60 years ago. The electronics has improved considerably since then. So anyway, that's going to finish it for me for today. I'm going to, if I'll review the comments. If it looks like this was useful at all, I'll probably do another one on reference frames and Coriolis effect. I'm going to do a hangout for sure on this problem that people have been working on, where the question is if I'll point it out, you have an hourglass, like an egg timer, and the sand is initially down in the bottom and you flip it. Okay, so you have all this sand that's running out, and before the sand starts running out, you weigh the hourglass. So this is a neat little physics problem for all of you out there to work on and think about. Is You have this hourglass sitting on a scale, and you measure some weight. Okay, I'll call it weight before. And then you open up the stopcock of the hourglass and let the sand fall. So the question is, while the sand is falling, does the weight of the hourglass change from the initial weight before the sand started pouring? And if so, is the weight during the pour greater than the initial weight? Is it less than the initial weight? Or is it equal to the initial weight? Does the weight of the hourglass change during the time that the sand is pouring down from the upper bulb to the lower bulb? That's the question. I have it figured out mathematically, and I will present that. All I can say is that my initial thoughts on this were pretty much spot on, and I think the results will surprise many of you because there's some amount of intuition that people have been using on this that is a bit incorrect. But think about it. It's a fun problem. And see what you come up with. And in the next Hangout, or I might even just do a video, I will present my analysis of it using physics. So I wish you all well out there. I'm going to pin up this paper and zoom in on it. And so you can see what it's all about. And I wish you well. Have a good evening. And until next time, if there is a next time, we'll see how it goes. So, so that's the first page of the paper. Now I'll leave this hang out for a while, so you people that are commenting can continue talking to one another, carry on your conversation. Oh, I'm also going to mention here that in another week or two, I'm going to be doing a video and probably a hangout too regarding a communication link calculator that all of you can use. I'll be hosting it on my company website. Cordis and I have been working on this, and it's an improved version of the Pasternak calculators that steps you through all the pertinent data that you need to input to get the what they call path loss on a communication link to see whether or not you can detect the received signals. Of course, all of you know that as a signal goes out into space, it disperses, it spreads out because of the 1/r² law. And this gives what is called an intrinsic path loss. But that's countered by your antenna gains, both at the transmitter, the receiver, and your receiver sensitivity and the transmitter power. And in our calculator, I've been working on data. We have one set of data up in the calculator. We have some examples that you can click on, and it'll automatically fill the fields with the proper data so that you can see what kind of return signal you get. Finished the Apollo 11 in 1969. We end up getting about a signal to noise ratio of the TV signals of about 10 decibels, which is more than enough. And I'm working on the Mars rover and the moon bounce signals and Voyager 2 to show that deep space communication is not only possible, but is very easy to pull off. Well, I shouldn't say very easy, but with modern equipment, it's not insurmountable. Voyager 2 is currently a little over 100 astronomical units away from the Earth, and we're still communicating with it. And we will probably be able to do so for, based on signal strengths, we'd be able to possibly do it for another decade as it's traveling out into deep space. But we're not going to actually be able to do it because by the time it gets out another 10 years, it's going to be so far away from any light sources that it's no longer going to be able to charge its batteries. The sun will be too far away, the intensity will be too low, and it'll just go dead. But if there was a way to charge the batteries, its useful life would be over another 10 years in being able to receive its signal. Like I said, it's about it's close to 3 times the radius of the atmosphere out, or not the atmosphere, but the solar system. It's at about, I think, around 120, 130 astronomical units, with an astronomical unit being the distance from the Earth to the sun. But as far as moon bounce goes, that's very easy to do. Hams do it all the time. And I'll be showing you how easy it is using 2 meters and 6 meter ham bands. The Globebuster guys just totally botched that one up. I've seen this Bob Nodal of Globebusters twice botch up the use of the Pasternak calculator. He ended up both times being off by 6 orders of magnitude, or 60 dB. It's rather embarrassing that someone that claims to be an RF engineer could botch it up so bad. Of course, he's not an engineer. I've already proven that. At best, he might be a wire puller for some satellite installation company, but he certainly doesn't know how to use space-link calculators. That much he's shown twice on Globebusters. The first time he talked about putting transmitter power in on the ham bands of 2,000 watts with 80% efficiency. And in his final numbers, he failed to put that in. And on the second attempt, he had the transmitter power right, but he failed to put in the receiver sensitivity. It's pretty embarrassing. But anyway, all these deep space communications, moon bounce, and communicating with the Mars rover is very possible, easy to do. The signals, though they're weak, they're not that weak that we can't detect them because we have 70-meter dishes, very high gain antennas here on Earth, and signal processing capability. Plus, the data rates are very low, like on Voyager 2. It's only about 160 bits per second. But we can still communicate with it, even though the signal is down. It's like at around 10 to the minus 20th watts that we're receiving here on Earth. And even though it's that weak with the receivers, the receiver sensitivities that we have, you know, with the gallium arsenide or silicon germanium front ends cooled down into liquid nitrogen with these high gain dish antennas, it's not an iffy proposition. The communication is very possible, and it's done daily. If you go to the JPL site, you can see that throughout the day, every day for a period of time, the Madrid 70-meter dish is communicating with Voyager 2, which is about 120 astronomical units from the Earth. The deep space communication is not a hoax. It's very real and successfully accomplished every day. So I'm done here. I'll just let it sit up here for about another 10 minutes so you guys can continue talking amongst yourselves, and then I will shut down the Hangout. Good boy, how you doing, huh? You have fun outside, huh? Be careful. Be careful. Come on. Oh, not there. Come on. No, no, stay. You people out in the chat know I will shut the hangout down at the top of the hour. It's 3:51 p.m. here right now, Central Daylight Time. I will shut down at 9 minutes from now. 5 minutes from now, I'm going to talk a little bit about my $20,000 challenge to flat earthers. I just received a letter on Friday from the bank, the trust company in Colorado, certifying the funds. And I'll show you that letter with the accounts, of course, deleted. The account number is deleted. But I'll talk a little bit about my $20,000 challenge to the flat earthers to prove that the earth is flat and motionless. The money is real. The challenge is real. It's up to you to claim the money. Shoot, what happened here? Okay, to all y'all people out there, this is the beginning of my $20,000 challenge to the flat earthers. This is the account that I have set up. This, as you can see, there's $27,381.13 in this account. 20,000 of it will be used for the flat earth challenge to prove that the earth is flat and motionless. I will within the next week do a video on the details on the rules and for setting up a judging panel. But the money is real, the challenge is real, and so it's going to be up to anyone out there to try to claim it by submitting proof. Two parts to the proof: one, that the earth is flat, and it is also motionless. The rules are basically going to be not much different than some of the rules that were set up by a Flat Earth Challenge to Glovers, set up by Eric DeBay and a few others. And the money there isn't real, but this money's real. It's really there, ready to be claimed. The challenge is going to last until June 1 for someone to claim it. There will be expectations as far as proof, of course, that just submitting a photograph and saying, look, the earth is flat, that's not going to cut it. You're going to have to submit some data, an analysis of the data, and it isn't going to be sufficient just to submit a video or photographs on one part of the earth. You're going to have to show this probably at least 3 different spots, space at least 300 miles apart. It's easy to find an unusual viewing spot like Ranky Flat Earth has done in the channel between England and Ireland. That isn't sufficient. Just finding one spot that can have unusual atmospheric conditions that might make it look like the earth is flat is not going to be sufficient. You're going to have to at least show that there are at least 3 different spots on the earth that this is true. And then there's also being able to show that the earth is motionless. These aren't impossible tasks, but it's going to take more than just submitting something from Eric Dubé's 200 proofs or some other bogus information that's out there. It's going to take some real work. Basically, you're going to have to, if you're going to do some measurements with auto levels, theodolites, or pictures, you're going to have to be able to show that this is true over a distance of at least 100 miles, not just 20 miles or 30 miles. It's easy to find places on the Earth over a distance of 20 miles in which to make things look like it's flat, but it's pretty much going to be impossible to do that over a 100-mile distance. So anyway, that's it, folks. We're going to shut her down. Enjoy your afternoon, and until next time. Hey, Con, want to say hello? Con, come on. Come here, Con. Come on. Hey. Come on. Here. Let's see, where is Con? Con. Here. Oh, he's heading. Come on, Con. Oh, there. Come on. Here. Come on. Come on. Come on, Con. Come on. Come on. Let's go. Come on. Yeah, he's hiding around the corner. He's not sure what to make of this. Come on, Con. Hey. Where are you? Come on, Con. Hey. Look. Come on. Come on. Come on. Let's go. Come on. Let's go, Con. Come on. He's suspicious. He's not sure what to make of this. Come on, Con. Let's go. Come on. Hey. Come on. Hey. Come on, Con. Here. Come on. Hey, Con. Come on. Well, I guess he's camera shy. Anyway, I'll catch you all later. Have a good afternoon. Huh? What do you think, Con? Huh? You gonna come? Come on. No. Come on. Huh? Oh, well.